Hello everyone, welcome to the 6th episode of me learning Rust. Today we'll do chapter 4 of the book, titled Ownership. So, let's begin. Ownership is Rust's most unique feature and has deep implications for the rest of the language. It enables Rust to make memory-safe guarantees without needing a garbage collector. So it's important to understand how ownership works. In this chapter, we'll talk about ownership as well as several related features, borrowing, slices, and how Rust lays data in our memory. Okay, but that means basically for me that there is no runtime component like a garbage collector that runs and makes sure that the memory is conserved, that all the checks that Rust does are compile time checks, and that means zero overhead when dealing with memory. Except maybe built-in things, but we'll see. Let's continue. Okay, what is ownership? Ownership is a set of rules that govern how a Rust program manages memory. All programs have to manage the way they use a computer's memory while running. Some languages have garbage collection that regularly looks for no longer used memory as the program runs. In other languages, the programmer must explicitly allocate and free the memory, like in C. Rust uses a third approach. Memory is managed through a system of ownership, with a set of rules that the compiler checks. If any of the rules are violated, the program won't compile. None of the features of ownership will slow down your program while it's running. Okay, basically what it said in the previous page. And because ownership is a new concept for many programmers, it does take some time to get used to. The good news is that the more experienced you become with Rust and the rules of the ownership system, the easier you'll find it to naturally develop code that is safe and efficient. Keep at it. Okay. When you understand ownership, you'll have a solid foundation of understanding the features that make Rust unique. In this chapter, you'll learn ownership by working through some examples that focus on a very common data structure, strings. Well, this is really good. I was expecting to get strings much later in the book, because I didn't understand completely what we had in chapter 2. So the stack and the heap. Okay, I'll go over it just for brevity's sake, and non-brevity's sake actually. But many programming languages don't require you to think about the stack and the heap very often, but in a systems programming language like Rust, whenever a value is on the stack or the heap, affects how the language behaves and why you have to make certain decisions. Part of the ownership will be described in relation to the stack and the heap later in this chapter. So here is a brief explanation in preparation. Both the stack and the heap are parts of memory available to your code to use at runtime, but they're structured in different ways. The stack stores values in the order it gets them and removes the values in the opposite order. This is referred to as last in, first out. Think of a stack of plates. It's just explanation of what a stack is, right? Let me just skim through. Okay, basically it explains what a stack is, what a heap is, that the stack comes with a program, that it's like a stack of papers, that usually, I don't know if it says so, but small parameters go into the stack, and the heap you have to allocate, you have to manage available memory, manage the chunks of memory. In the stack, you just add and remove, add and remove. This is all you do with the stack. Also, functions, function arguments go on the stack, and other flags for compiler and return locations also go on the stack, while the heap is just a chunk, actually many chunks of memory that you can use for whatever reason you want. Usually, I don't think it says here, but usually the stack is limited to relatively small values in orders of megabytes, and you can go and have a stack overflow if you use too much function nesting or recursion, or just use a lot of parameters on the stack. For example, if you define like a big array on a stack, then it will create an overflow of the stack. So let's continue. If you want to read more about stack and heap, you're welcome to do so. I don't think that there's something here that's really Rust relevant. I didn't see the word Rust even once here, except in the beginning. So let's just jump ahead to ownership rules. First, let's look at the ownership rules. Keep these rules in mind as we work through the examples that illustrate them. Each value in Rust has an owner. There can be one owner at a time. When the owner goes out of scope, the value will be dropped. So basically, it's like smart pointers up until now. Only they're compile time instead of runtime as in C++. Now that we're past basic Rust syntax, we won't include all the function main, code, and examples. So if you're following along, make sure to put the following examples inside a main function manually. As a result, our examples will be a bit more concise, letting us focus on the actual details rather than boilerplate code. Okay, so let's just start a new project. We call it chapter 4. And then go, open code to chapter 4. Excellent. Let's go here, main, turn this off, turn this on, and continue. So, as the first example of ownership, we'll look at the scope of some variables. A scope is arranged within a program which an item is valid. Take the following variable, hello s. The variable s refers to a string literal, where the value of the string is hard-coded into the text of our program. I wonder if it means the actual text part of the binary or not. We'll see later. The variable is valid from the point at which it's declared until the end of the current scope. Listing 4.1 shows a program with comments annotating where the variable s would be valid. So basically, it's usual scoping, right? If you define something within a scope, once you go out of scope, you can no longer use this s semantically. I guess the memory is still there when you pop out, but you cannot safely rely on it. In other words, there are two important points here. When s comes into scope is valid, it remains valid until it goes out of scope. Makes sense. At this point, the relationship between scopes and when variables are valid is similar to that in other programming languages. Yes. Now we're build on top of this understanding by introducing the string. The string type. To illustrate the rules of ownership, we need a data type that is more complex than those we covered in the data types section of chapter 3. The types covered previously are of known size, can be stored on the stack, and popped off the stack when their scope is over. Yeah, one thing to say about the stack, that you have to know the size of an object that you put on the stack. If there's something of unknown size, there is no way of putting it on the stack, because you have to move the top of the stack a number of bytes. So if you don't know how many bytes you have to move, you can't do it. I don't think there is a mechanism in any language I know that allows you to even hack this. Like, you have to specify the size of the object you allocate on the stack. Okay, let's move on. Where was I? Okay. Okay, but we want to look at data that is stored on the heap and explore how Rust knows when to clean up the data, and the string type is a great example. We'll concentrate on the parts of the string that relate to ownership. These aspects also apply to other complex data types, wherever they are provided by the standard library or created by you. We'll discuss string more in depth in chapter 8. Okay, so I guess all the encoding, decoding won't be discussed here, but we can wait. We've already seen string literals, where a string value is hard-coded into a program. String literals are convenient, but they aren't suitable for every situation in which we may want to use text. Yes, string literals, we know in advance their size, and that is why we can actually define a string literal within the scope of the code. Like if I'm doing something like this, this is defined on the stack, because it knows that the size here is 6 bytes or something. I don't know how Rust encodes strings, but usually in C you have a 0 at the end that is not represented when you write this. But actually we can test this. Let's see if there's my string length. There's length. Let's try to run this. And we get 5. So it says that the size of the string is 5. Interesting. What if I'm doing something like this? Let's say 6. Yeah. Okay. Great. Let's continue. One reason is that they're immutable. Another is that not every string value can be known when they write our code. For example, what if we want to take user input and store it? For this situation, Rust has a second string type, which is string. So this is so str with lowercase letters is the literal, and if you want a string object, then it's a string with a uppercase S. Okay, this type manages data allocated on the heap, and as such, it is able to store an amount of text that is unknown to us at compile time. You can create a string from a string literal using the from function. So let's just use this now. From, and now it's a string. Still has a length. Let's check the length of the string right now. Still 5. Okay. Let's continue. So we've created a string object from a string literal. The double colon operator allows us to namespace this particular from function under the string type rather than using some sort of name like string from. We'll discuss this syntax more in the method syntax section of chapter 5. And when we talk about namespacing with modules in paths and referring to an item in the model tree, very catchy chapter name. Okay, this kind of string can be mutated. So, mutable. Oh, not mutated. So let's define a mute, and then we can push string. I guess it appends something. It's my string. Let's just call it S to be like the example. It push string world, and that probably just appends to the string, and then we want to print this. Let's print just S. C cargo run. Now we have hello world. Excellent. So that's so what's the difference here? Why can string be mutated but literals cannot? The difference is in how these two types deal with memory. So let's just make sure that I can do a mutable my string, which is hello. Yeah, it says remove this mute. A mutable mute can be used in several situations. The first mutable verb, no. Okay, it's unused mutable. So let's see if I can do my string push. There's no push, but I can mutate it somehow. Is there anything? Put maybe. Set. Replace. A with B. What it says, unused return value. It's still warning, but it allows me to have this literal as a mutable type. Let's just try to run this. Oh, sorry, I have to save first. So I'm running this and it works. It just complains about it. Yeah, oh yeah, let's just do this. And yeah, it lets me define this as immutable. That, yeah. So I don't understand. Okay. String can be muted, but literals cannot. Here, well, maybe I can't mutate it. Maybe it just creates a copy or something. Maybe it's more implicit. That's bad. That's like I would expect more explicit definitions in Rust. But let's remember this and continue. Okay. In the case of string literals, we know that the contents at compile time. So the text is hard-coded directly into final executable. This is why string literals are fast and efficient, but these properties only come from string literals immutability. Unfortunately, we can't put a blob of memory into the binary of each piece of text whose size is unknown at compile time, and whose size might change while running the program. So yeah, as I suspected, the string literals go into some special string section in the executable. I guess what they meant by that the literals are immutable is that the literal itself, not as a object of Rust, but as an object in the executable, is set and cannot be changed. Like when I write this hello will be inside the executable. I cannot change this specific hello. I can make copies, I can make changes, I can do whatever I want, but the initial hello is immutable. Okay. With a string type, in order to support a mutable, growable piece of text, we need to allocate an amount of memory on the heap, unknown at compile time, to hold the contents. This means the memory must be requested from the memory allocator at runtime, and we need a way of returning this memory to the allocator when we're done with our string. The first part is done by us. When we call a string from, its implementation requests the memory it needs. This is pretty much universal in programming languages. Well, yeah, generally speaking. However, the second part is different. In languages with a garbage collector, the garbage collector keeps track of and cleans up memory that isn't being used anymore, and we don't need to think about it. In most languages without a garbage collector, it's our responsibility to identify when the memory is no longer being used and to call code to explicitly free it, just as we did to request it. So like C, C++, I do malloc or new and then free or delete. In Java, I just stop using this object, and when all the references go out of scope, it just deletes this object and manages this memory. I don't think it frees it specifically in case of Java or other languages. It just moves it back into some sort of pool of memory. But it's marked as unused. Okay, doing this correctly has historically been a difficult programming problem. I don't agree with it. You just have to be thorough. If we forget, we'll waste memory. If we do it too early, we'll have an invalid variable. If we do it twice, that's a bug too. We need a pair of exactly one allocate with exactly one free. Rust take a different path. The memory is automatically returned once a variable that owns it goes out of scope. Here's a version of our scope example from listing for one using string instead of a string literal. So we create a scope with a string literal. Yeah, I don't think there's any point in writing this because it does nothing. But yeah, we define a string, it allocates memory, and here it probably deallocates. I think it's basically Rust itself programs a free function here. Yeah, just instead of me doing like this, something like this, it's just doing this and then doing free s, which is invalid, or is it? There's no error. Let's see. No, yeah, there's an error. I always forget to save. So instead of doing this, when I do this, it automatically marks that it should free the S here, and then does it. There are some methods in other languages, like I can do something like defer free S. So the second I define I allocate this memory, I say, okay, when you go out of scope, just free this memory. This is maybe something similar to what Rust does behind the scenes. So let's continue. There is a natural point at which we can return the memory to our string. There is a natural point at which we can return the memory our string needs to allocate to the allocator. When S goes out of scope, when a variable goes out of scope, Rust calls a special function for us. The function is called drop, and this is where the author of a string can put the code to return the memory. Rust calls drop automatically at the closing of curly bracket. So this is interesting. That means that Rust supports allocation and deallocation and memory, maybe pointer things. If you need to implement this drop, then it means that you have to know the memory behind it, which I think is good. I think it gives power. I hope that there is some guide and some tests that you can run within Rust to make sure that you do everything okay. But the fact that it's very defined is already good. I hope it will not become as convoluted as the destructures in C++, which is a big mess. You'd never know the order, or you can know the order, but it's very convoluted. You have to go to documentation of the compiler of the language specifications to understand how the structure will run, especially with the static values. So I don't want to go into this rant. Okay. Note, in C++, this pattern is of deallocating resources at the end of an item's lifetime. It's sometimes called resource acquisition is initialization. The job function in Rust will be familiar to you if you used this structure, what I said before. This pattern has profound impact on the way Rust code is written. It may seem simple right now, but the behavior of code can be unexpected in more complicated situations when we want to have multiple variables use the data we allocated on the heap. Let's explore some of those situations now. This is not a good sign that you say it's going to be convoluted when you're advertising this language as very safe. Okay. Multiple variables can interact with the same data in different ways in Rust. Let's look at an example using an integer in listing for 2. So yeah, let's just write this down. I want to follow if it's very convoluted. I do want to test it while recording. Yeah, okay. So we have this, x is equals 5, and then 1 is equals x. Great. We can probably guess what is it doing. Bind the value of 5 to x, then make a copy of the value in x and bind it to y. We now have two variables, x and y, and both equal 5. This is indeed what is happening because integers are simple values with a known fixed size, and these two 5 values are pushed into the stack. And now let's look at the string version. So we do s1 string from hello, and then s1 s2, right? Okay. So now they're both string. Just a warning that I'm not using it. Yeah, this looks very similar, so we might assume that the way it works would be the same. That is, that the second line would make a copy of the value s and bind it to s2. But this isn't quite what happens. Let's go. Take a look at figure 4.1 to see what is happening to string under the covers. A string is made up of 3 parts, shown on left: a pointer to a memory that holds the contents of the string, a length, and a capacity. This group of data is stored on the stack. On the right is the memory on the heap that holds the contents. Okay, so this is on the stack, this is on the heap. Basically, we have 3 values on the stack. We have a pointer to the data, the length of the data, and the capacity. Capacity, I don't think they're right here. The capacity is the amount of memory allocated for this string. Usually when you have something with the variable size, you don't want to allocate memory each time you want to append some memory, because allocation make you go to kernel space and then do an allocation. It's better to just have some spare memory around, and when you want to increase the length of the string, you just add it until you reach the capacity, and then you just double the capacity or do some other thing that makes it bigger, not by 1 but by some factor. That makes it faster to do some dynamic vectors, basically, if you look at a string as a vector of characters. So here I'm really glad that there is a length parameter stored here. Yeah, because with C strings you don't have a length. You just have to, in order to know the length of a string, of a C string, you have to scan and reach the character 0 to know the length, and here you already have the length. Yeah, I prefer it that way when I implement my own strings with different platforms. I like to use this kind of notation. Okay, so the length, and this is the memory, right? I point to this memory, and by this diagram there is no 0 at the end. So yeah, you always use the length of the string to know how many bytes you have in on the heap. Okay, the length is how much memory in bytes the content of the string are currently using. Great. The capacity is the total amount of memory in bytes that the string has received from the allocator. The difference between length and capacity matters, but not in this context. So for now, it's fine to ignore the capacity. When we assign S1 to S2, the string data is copied, meaning we copy the pointer, the length, and the capacity that are on the stack. We do not copy the data on the heap that the pointer refers to. In other words, the data representation in memory looks like this. Yeah, that makes sense. Basically, when you copy within the scope, then it copies what's on the stack and not what's in the heap. You have to be specific. Probably there is some clone or copy function or a method for strings that actually does copy this and then creates a new object on the stack with a different pointer, with the same length and maybe capacity. You can't know. Maybe the capacity will be set strictly to the size. The representation does not look like figure 4.3. This, which is what memory look like if Rust instead copied the heap data as well. This is what I'm saying. I don't know about capacity, but it says not think about capacity, so we're not thinking about capacity yet. If Rust did this, the operation S2 equals S1 could be very expensive in terms of runtime performance if the data on the heap were large. Yeah, this is one of the reasons that you use references. Basically, if you don't want to copy huge amounts of data, especially in read-only situations, even when you have to read and write, you sometimes want to pass around references. Yeah. Earlier we said that when a variable goes out of scope, Rust automatically calls the drop function and cleans up heap memory for that variable. But figure 4.2 shows both data pointers pointing to the same location. This is a problem. When S2 and S1 go out of scope, they will both try to free the same memory. Yeah, this is a problem with the structures. If you when you have the move and copy operators, and if you make a mistake there, you're gonna have some errors that might not even pop up in the beginning. I'm talking about C++ right now. Okay, this is known as a double free error, and it is one of the memory safety bugs we mentioned previously. Freeing memory twice can lead to a memory corruption, which can potentially lead to security vulnerabilities. Usually just throws some sort of error at runtime and crashes your program. To ensure memory safety, after the line S2 equals S1, Rust considers S1 as no longer valid. Interesting. Therefore, Rust doesn't need to free anything when S1 goes out of scope. Check out what happens when you try to use S1 after S2 is created. Okay, interesting. Print line S1 and we have S1. Sorry. Can we use like this? It says that borrow of moved value S1, right? Borrow of moved value S1. So there's an error, like it's no longer valid. Value borrowed here after move. Okay, this is the error that we get. Let's hear an explanation. If you heard of terms shallow copy and deep copy while working with other languages, the concept of copying the pointer length and capacity without copying the data probably sounds like making a shallow copy. But because Rust also invalidates the first variable instead of being called a shallow copy, it is known as a move. In this example, we would say that S1 has moved into S2. So what actually happens is shown in figure 4.4. Okay, makes sense. So now I can't use it, and if I use S2, this should work. Okay, great. Let's run this. Yep. That solves our problem. With only S2 valid, when it goes out of scope, it alone will free the memory, and we're done. Yeah, it's a smart way of doing this. And also, like, if you throw errors, compile errors, if you use S1 after it has been moved, this is a really good way of avoiding this type of double free error. In addition, there is a design choice that's implied by this. Rust will never automatically create deep copies of your data. Therefore, any automatic copying can be assumed to be inexpensive in terms of runtime performance. Yeah, like if Rust is really doing this, then it's good. It means that whenever you copy data, the maximum amount of things added to the stack will be the size of the structure of the data type you're using, and it will be consist only of primitive types in Rust, which is like booleans, integers, characters. Basically, we looked it over a couple of episodes before. Okay. Variables and data interacting with clone. Okay, so clone is probably the copy thing. If we do want to deeply copy the heap data of the string, not just the stack data, we can use a common method called clone. We'll discuss method syntax in chapter 5, but because methods are a common feature in many programming languages, we've probably seen them before. Here is an example of clone. So if I'm doing clone, that means I can use S1. Yeah, let's just use them both and print hello, hello. Hello, hello. This works just fine and explicitly produces the behavior shown in figure 4.3, which is this. Where the heap data does get copied. I really like this. I really like this approach that when you do operations with the heap, you know that something is going on with the heap. I'm trying to think of examples where it won't be the case. Like if I have maybe nested structures. No, but even with nested structures, you do know the size that is on a stack. So yeah, so every time I do an equal sign, just an equal sign, I'm just copying and allocating stack objects. It will never be something from the heap, and I have to run a specific command. Probably there is some sort of rules and syntax that I can look. Well, yeah, hence don't say anything, but yeah, but I know that if I do from, probably allocates. If I do a clone, it probably allocates. Yeah, if I don't need to allocate, I probably will not implement a clone method, and that is how I will know that nothing happens on a heap. So no implicit heap operations. This is important. Okay. When you see a call to clone, you know that some arbitrary code is being executed and that code may be expensive. It's a visual indicator that something different is going on. Okay, this is more general. Stack-only data copy. There's another wrinkle we haven't talked about. This code using integers, part of which was shown in listing for 2, works as valid. But this code seemed to contradict what we just learned. We don't have to call clone, but x is still valid and wasn't moved to y. But I think we discussed it. It's because it's on the stack and it's known size. Okay. The reason is that types such as integers have a known size at compile time and are stored entirely on a stack, so copies of the actual values are quick to make. That means that there is no reason we would want to prevent x from being valid after we create the variable y. In other words, there is no difference between deep and shallow copying here, so calling clone wouldn't do anything different from the usual shallow copying. We can leave it out. So wait, so let me just make sure. So I have actually a clone for integers. Yeah, and let's see if it has some warning of a clone. What it says, if this is intentional, prefix with underscore. Yeah. Okay, it works, and it's not even a warning. Okay. Oh, well, I would have put a warning here because it's redundant, but whatever. Rust has a special annotation called the copy trait that we can place on types that are stored on the stack as integers. We'll talk more about traits in chapter 10. Okay, traits. So I have no idea what they are. If a type implements the copy trait, variables that use it do not move, but rather are trivially copied, making them still valid after assignment to another variable. So I have to define something as a trait in order for this to work. Like if it's not a trait, then I will get this error. If it's a trait, like an integer in the previous case, this will work. Okay. Rust won't let us annotate a type with copy if the type or any of its parts has implemented the drop trait. If the type needs something special to happen when the value goes out of scope and we add the copy annotation to the type, we'll get a compile time error. To learn about how to add the copy annotation to your type, implement the traits, see derivable traits in Appendix C. So this is actually interesting. That means that the compiler also controls about me defining my own types and objects by making sure I either go with a copy trait for simple stack allocated objects, or I implement the drop method for some heap or end-of-life operations I want to do with an object or data structure. We'll find out which in the future. So what types implement the copy trait? You can check the documentation for a given type to be sure, but as a general rule, any group of simple scalar values can implement copy, and nothing that requires allocation or is some form of resource can implement copy. Here are some of the types that implement copy. All the integers, all the Boolean types, true, false, floating points, characters, tuples, if they only contain types that also implement copy, okay? And this is important. And if we have a tuple of strings that we cannot make them, we cannot copy them or clone them, or we have to clone them. Let's try something. T equals let's have tuple, yes, and t1 equals t, equals t, right? And then we'll do t and t1 doesn't, right, t and t1 doesn't implement display. Okay, now the t1 is okay because it borrowed from t, and t is wrong. And if we do this, clone, this should work. Okay, and if, let's roll back. Now I have a tuple of strings. If I have a tuple of integers, then this should work. Okay, excellent. So yeah, we made sure that, let's just go back. We made sure that if we have a tuple of items that are stack only, that are copy, that implement the copy trait, then we can use them just after the equal signs. And if we have a tuple of strings or items that have the drop, that are not copy trait able, then we have to use the clone if you want to do this kind of copy. Okay. Ownership and functions. Okay. The mechanics of passing a value to a function are similar to those when assigning a value to a variable. Passing a variable to a function will move or copy, just as assignment does. Listing for 3 has an example of some annotation showing where variables go into and out of scope. So, let's look at this example. We have two functions. We have the take ownership that gets some string comes into scope. It prints the string, here some string goes out of scope, and drop is called. The backing memory is freed. Makes copy, some integer I. Here some integer goes out of scope, nothing special happens. Okay, so this is when memory is freed, and this is not. Let's have a string, takes ownership, s value moves into the function, and is no longer valid here. Wait, I need to test this. Okay. So now if I want to print s, I should get an error, right? Oh, sorry. This should be an error. Borrowed move. Okay, this is actually great. Even if I don't know what happens, the fact that I pass this variable as a and it takes ownership, it already invalidates everything that comes afterwards. So I need to do something with this function in order to keep s valid further in the code. So I'll keep this example. Probably the next paragraphs will let us see how we fix this. Okay, if we try to use the s after a call to take ownership, Rust would throw a compile time error. These static checks protect us from mistakes. Try adding a code to main that uses s and x to see where it breaks. So I guess if I'm using x here, nothing interesting will happen, right? This is because x has a copy trait. Great. Return values. It doesn't say how we fix this. Okay. Returning values can also transfer ownership. Listing for 4 shows an example of a function that returns some value with similar annotation as those in listing for 3. Okay, so let's see what we have here. We have here gives ownership a string. It creates a string and then returns it. Let's just copy this function further down. Move this. So we have this function. Okay, great. So this is just, it creates the function and then returns the string. And this is takes and gives back. Okay, this is takes and gives back. And then the code. Let's just copy and go over the code. Okay, so here we have the give ownership, and it runs this function. It creates a string on the stack in a local scope, then it returns and moves out of the calling function. That means that it gives the ownership of the memory back. But I would have... So this does not use the drop. I think the fact that I'm returning this variable prevents the drop from running. Then I get the variable here into S1, the string. Then I create an S2 in the scope, and then I take and give back S2. So I'm passing S2 to this takes and give back. The takes and give back just gets the string, makes a shallow copy, and then gives it back. That means that it never runs the drop as well. So I'm guessing if I'll do all the prints, I'm not... wait, I will get an error, I think, with S2. Let's see. I have S1, S2, 3. I forgot about quotation marks. So the error is with S2 because here I'm passing the ownership. So this is invalid. And then when I come back from this function, the S3 owns the memory that S2 had. This is very similar to say S3 equals S2. But I go through a function call. Okay, I think I'm getting this, but I still don't know how to do this properly. How I can pass a function, how I can pass a string to a function, and then continue using it. Like, how can I do this, basically, and still continue using S2? So let's read about this, if there is a way to do this. Okay, the ownership of a variable follows the same pattern every time. Assigning a value to another variable moves it. When a variable that includes data on the heap goes out of scope, the data value will be cleaned up by the drop unless ownership of the data has been moved to another value. Okay, so this one moves the ownership back, so this is or becomes invalid. The sum string is already an invalidated because it was borrowed. So, and the owner is the variable that receives the return of give ownership, as well as here it takes this A string, invalidates S2 right here, and then here it invalidates the A string and moves the ownership back to S3. Not back to S3, but to S3. And this is why S3 is valid and S2 is invalid, and they both point to the same memory. Basically, S2 used to point to this exact memory. Okay. Well, this works. Taking ownership and then returning ownership with every function is a bit tedious. Yes. What if we want to let function use a value but not take the ownership? It's quite annoying that anything we pass in also needs to be passed back. If we want to use it again, in addition to any data resulting from the body of the function that we might want to return as well. Rust does let us return multiple values using a tuple as shown in listing 4.5. So I can return a tuple. Let's just run this. So we have I create a string and then I calculate length. I get the string here. I get the ownership. I calculate the size and then I give back ownership as the first parameter and size as the second parameter, and then it will print then S2 is valid, S1 is invalid. Let's run this code, see that it's valid, and then I'll try to add S1 to see that it is not valid. Yeah, it's an error. Okay, as expected. But this is too much ceremony and a lot of work for a concept that should be common. Luckily for us, Rust has a feature for using a value without transferring ownership called references. Next page. References and borrowing. The issue with the tuple code in listing 4.5 is that we have to return the string to the calling function so we can still use the string. So basically it says when I'm passing the ownership to a function, the function needs to return the ownership of the variable for me to continue using it under a different variable. I guess if I'm doing something like this, it will still work, right? Because of shadowing. Let's run this. So this worked because of shadowing, but we need to remember that this S1 and this S1 are different variables, just have the same name. Okay, so the issue with the tuple code in listing 4.5 is that we have to return string to the calling function so we can still use the string after the call to calculate length. Because the string was moved to calculate length, instead, we can provide a reference to the string value. A reference is like a pointer in that it's an address we can follow to access the data stored at that address. That data is owned by some other variable. Unlike a pointer, a reference is guaranteed to point to a valid value of a particular type for the life of that reference. It's like probably references in C++, which is better than just passing everything as a pointer to C, because when you pass a reference, the compiler knows that there is a data behind it, and it can also fix and do some optimizations in regard to pointer aliasing. If you don't know that, you can read about this. I'm not going to go into this. Okay, so here is how you define and use a calculate length function that has a reference to an object as a parameter instead of taking ownership of the value. So I don't want to copy this. I want to just read. So how the function changes, I just add a reference here, right? And I return a useSize. And I just return a size. I guess I can do something like, let's do it as len, right? This is exactly what they do as well. In here, I just have to do this. And though I didn't, I need to say that I get the passes as a reference. So if I pass this as a reference, the ownership probably does not go to the calculate length, and this is still valid. So I can use this exact S1 and the return type length. I put the length. Let's save it. Let's run this to get here. Hello is 5, and let's read on. First, notice that the tuple code in the variable declaration and the function return value is gone. Okay, in the return value. Okay. Second, note that we pass ampersand S1 into a calculate length. I'll call ampersand ref from now. And in its definition, we take the ref string rather than string. This ampersands represent references, and they allow you to refer to some values without taking ownership of it. So great, now we have a mechanism that I can pass variables that are on the heap that have some complex functionality just as a reference, just as passing a pointer in the C++, and as a reference in C++. So this is what we do. Basically, the S that we have here is actually a pointer to the S1 on the stack in the main scope. And we use this, we mutate this, do whatever we want, and then we just, when we go out of scope, the S itself, this pointer, goes out of scope, but this is still on the stack in the main scope. So it's still valid. Great. The opposite of referencing by using ampersand is dereferencing, which is accomplished with the dereference operator asterisk. Just like in C++. We'll see some uses of the dereference operator in chapter 8 and discuss details of dereferencing in chapter 15. Let's take a closer look at the function call here. Okay, the ref S1 syntax let us create a reference that refers to the value of S1 but does not own it. Because it does not own it, the value it points to will not be dropped when the reference stops being used. So this one does not run the drop function. So if something is a reference, the drop function will not be used on it. Okay, this is what we remember. Likewise, the signature of the function uses ampersand to indicate that the type of parameter s is a reference. Let's add some explanatory annotations. I'm not going to do this. The scope in which the variable s is valid is the same as any function parameter scope, but the value pointed to by the reference is not dropped when s stops being used, because s doesn't have ownership. When functions have references as parameters instead of the actual values, we won't need to return the values in order to give back ownership, because we never had ownership. Okay, we call the action of creating a reference borrowing. As in real life, if a person owns something, you can borrow it from them. When you're done, you have to give it back. You don't own it. So what happens if we try to modify something we're borrowing? Try the code in listing 4.6. So if let's copy it and then look at it. So now we have a function change that tries to push string, and it's an error that says you cannot change a mutable reference. Okay, interesting. Probably because I'm trying to change the value, the stack value. I'm changing the length or capacity here. Yeah, I think if I will try to do something that changes the memory in heap, it will not have an error when we talk about strings, because I don't know how to change characters. Well, maybe I do. Let's try some string. Let's just try location 2 equals a. Yeah, I don't think I can do it. It will be indexed by integer. Yeah, maybe there's something set, or no, replace. Yeah, I don't know how to do this. I don't know how to change a character in a string yet. So we'll test this. We'll see if this error is because we're changing the length or capacity potentially, and not the memory itself. So this is an error. Here is the error. We get similar error code, is mutable and behind the reference. It's a little bit different, right? No, pretty much the same. Just as variables are immutable by default, so are references. We're not allowed to modify something we have a reference to. Mutable references. Okay. We can fix the code from listing 4.6, allow us to modify borrowed value with just a few small tweaks that use instead of a mutable reference. So here I'm putting a mutable reference. That still doesn't work. And if I put here that it's a mutable reference, it works. First, we change s to be mutable. Then we create a mutable reference with mutable s. We need to change s to be mutable. Oh, forgot about this. Then we create a mutable reference with refmute_s. When we call the change function and update the function signature to accept a mutable reference with some string mute string, this makes it very clear that the change function will mutate the value it borrows. Okay, so now just when I call this, I'm saying, okay, I allow you to change the string. It still doesn't answer if I can change the content of the string without changing the size and capacity of the string. We'll have to test this out. I think in the string chapter we'll be able to do this. But for now, we don't know how to do this, and I do want to continue with this chapter. Okay. Mutable references have one big restriction. If you have immutable references to a value, you can have no other references to that value. This code that attempts to create two mutable references to s will fail. Okay, so I can't create two mutable references. do have an S already. So this will fail because I already have a mutable reference to this, and I can't have two mutable references. Makes sense. It's wait. Let's read, because I'm not sure how it makes sense. Why can't I do this? Maybe, yeah, if I'm doing some sort of threading, might be a problem, but with procedural code. Okay, well, let's read on and see if it says something about this. The error says that the code is invalid because we cannot borrow A as mutable more than once at a time. The first mutable borrow is R1 and must last until it's used in the print line. But between the creation of the mutable reference and its usage, we try to create another mutable reference in R2 that borrows the same data as R1. The restriction preventing multiple references to the same data at a time allows for mutation, but in a very controlled fashion. It's something that new Rustaceans struggle with because most languages let you mutate whenever you'd like. The benefit of having this restriction is that Rust can prevent data races at compile time. A data race is similar to a race condition that happens when these three behaviors occur. Two or more pointers access the same data at the same time. At least one of the pointers is being used to write the data. There is no mechanism being used to synchronize access to the data. So yeah, so in case of threading, this is very, very bad. When there is no threading, I don't think it will cause some serious issues. You might not know what to expect to get because you can pass the mutable variable. You can do something like, like asynchronous functions that might change things. But yeah, when we have to talk about parallelism when this is important. With no parallelism, this is, yeah, I don't see a reason why this should be an error. But okay, yeah, Rust is probably also thread safe by design. I hope so, or I don't know. But yeah, okay. Let's just know that we'll get an error if we try to have a mutable reference to the same parameter twice or more. Okay. Data races cause undefined behavior and can be difficult to diagnose and fix when you're trying to track them down at runtime. Yes. Rust prevents this problem by refusing to compile code with data races. As always, we can use curly brackets to create a new scope, allowing for multiple mutable references, just not simultaneous ones. So, okay, so I'm creating this reference temporarily. Then I exit the code. That means that this is no longer valid because it is outside of the scope. Yeah, okay. Rust enforces a similar rule for combining mutable and immutable references. This code results in an error. So we get here a mutable string, and then I have a reference of the string in R1, reference to string in R2, and then I'm trying to have a mutable reference to R3. Okay, that makes sense, because when I'm defining R1, I assume that I have only an immutable reference, that S will not change while I have this. So while I'm using R1, Rust actually prevents me from doing any changes to S. Makes sense. Or to this reference. Yeah, it makes sense. I can see a lot of errors coming from this. When you just pass R3 to some other function that does something that waits, even if you have like several threads, you don't know what's happening. Because R1 is an immutable reference, it assumes that it will be immutable, but somewhere else someone changes S, so I can read it and then do an operation, and between me reading and doing the operation, someone else can come and change the value, and then this string is no longer valid. And here is the error. Immutable borrow occurs here, mutable borrows here, and compiling and cannot borrow as mutable because it is also borrowed as immutable. Makes perfect sense. Phew. We also cannot have mutable reference while we have an immutable one to the same value. Users of an immutable reference don't expect the value to suddenly change out from under them. However, multiple immutable references are allowed because no one who is just reading the data has the ability to affect anyone else's reading of that data. Yeah, I can have like multiple reads. If it's immutable, I can do whatever I want, pass it around. But the second I mark it as mutable, all the immutable should be no longer valid because they're not immutable anymore. Someone else can change it. So it makes perfect sense that you would make this an error in Rust. Note that the reference scope starts from where it's introduced and continues through the last time that reference is used. For instance, this code will compile because the last usage of immutable reference print line occurs before the immutable reference is introduced. So we define R1, R2, we use R1, R2, then they no longer used after this, and then I defined S as mutable, and then I use it. That means that the program knows that R1 and R2 are no longer relevant after this line because no one uses them. I wonder how it does it with multi-threading. I think that the passing it in arguments does the check because of the like restrictions when passing arguments. I think it can deduce. Yeah, it can know. It can know when the parameter is no longer valid if I pass it. Because if I pass it as an immutable, what happens is it copies this data, and now it's interesting. If I pass it to a function, if I have a function, let's say even change, and I'm getting a string reference which is immutable, this should not work. Push string, this should not work. And let's just print it. Let's print it. Maybe it's not error because of the previous error. And we print some string. Yeah, and then I'm printing this S several times. Yeah, I'm printing this, let's say twice, or I'm doing something like this. R1, then we have R2 here. Oh, sorry. Wait. Let's see if this runs. Okay, this runs. So, well, maybe because I'm out of scope here. Let's try this. Will this run? Yeah. So I think we need to dig a little deeper, maybe later, to see exactly what's the thing here. Because when I pass the S, like when I pass R1 is this is a mutable, yeah, is a mutable string. I pass it as a reference, not as a mutable reference. So it casts down to an immutable reference. What if I'm doing this? This will be an error, but if I'm not running this, oops, sorry. This is what I wanted to do. Then I can't pass this because I have to pass a mutable string, and if I revert this here, this works. So I pass this. It's just a reference, but it copies the reference, so I cannot change the length and the capacity, and it can use this. So my suspicion from the beginning, I think, was right. I think that when we're talking about borrowing, we're only talking about items on the stack. So the Rust doesn't care if I change the content of the string itself. It only cares if I change the structure, the pointer, the capacity, and the length of the string. So as long as I don't do this, I can do this. I can pass on an immutable reference and then use immutable reference afterwards. Okay, this is even too much for me to understand. I think as we go along, we'll see what can be done. I do see the reasoning behind this generally. Yeah, you want to make sure no one passes something that can change in the future without knowing it could change in the future explicitly. Okay. The scopes of the immutable reference R1 and R2 end after the print line where they are last used, which is before the mutable reference R3 is created. These scopes don't overlap, so this code is allowed. The compiler can tell the reference is no longer being used at this point before the end of the scope. Even though borrowing errors may be frustrating at times, remember that it's a Rust compiler pointing out a potential bug early at compile time rather than at runtime and showing you exactly where the problem is. Then you don't have to track down why your data isn't what you thought it was. So yeah, give me a little headache, but I think when we start using this more, we'll understand more. I think when we go to multi-threading and more complex functions, then we'll be able to see this more clearly. But for now, I trust the compiler to stop me from doing something, and I think instead of trying to understand now all the scope of the borrow checker, I'll just do it by errors. I'll try to push it every time as much as I can until I get an error, and then learn from the errors. Okay, dangling references. I think we'll stop after this page. We'll peek out ahead, but we'll start. In languages with pointers, it's easy to erroneously create a dangling pointer, a pointer that references a location in memory that have been given to someone else by freeing some memory while preserving a pointer to that memory. In Rust, by contrast, the compiler guarantees that the reference will never be dangling reference. If you have a reference to some data, the compiler will ensure that the data will not go out of scope before the reference to the data does. So yes, every time you pass this, the drop will not work. I guess it also depends on the implementation of the underlying allocation code, because I can deallocate and free data on regular operations, probably. Or maybe there is some kind of mechanism when we'll talk about allocations within Rust to prevent even this. But as explained here, when I pass something by reference, no matter if it's a mutable or immutable reference, the pointer, I expect all the pointers to be valid pointers. Okay. So let's try to create a dangling reference to see how Rust prevents it. So this is the code to create a dangling reference. Let's copy it here. So we have dangle that generates a string, it allocates a string, and then it returns a reference to it because the string was defined here, and I borrow it outside, like the reference to nothing borrows the string. That means that S is still the owner, and when we go out of scope here, drop will work. So this should return, like if there was no error here, this should have returned an invalid pointer to reference to nothing. Let's run it and get the error. We get the error also here. Consider using this static, lifetime static. Okay, let's see. It's also says here. So expected named lifetime parameter. Don't know what this is. Consider probably this is lifetime parameter. Okay, this error message refers to a feature we haven't covered yet, lifetimes. We'll discuss lifetimes in detail in chapter 10, but if you disregard this part about lifetimes, the message does contain the key to why this code is a problem. The function return type contains a borrowed value, but there is no value for it to be borrowed from. Let's see. Yeah, this is the... I'm sorry, you can't see this. This is the error I'm getting here. Great. Maybe here also. Yeah, the error is here. So if I do the static here, let's see. Just see if it works. Now it works, and I have this. Okay. No, it still doesn't work. Okay. Well, we'll get to this in chapter 10. Okay, let's take a closer look at exactly what's happening at each stage of the Dangle code. So, yeah, this is what we said. There's a new string. We return a reference to string s, and here s got out of scope and dropped. Its memory goes away. Danger, because s is created inside Dangle. When the code of Dangle is finished, s will be deallocated, but we try to return a reference to it. That means that the reference would be pointing to an invalid string. That's not good. Rust won't let us do it. The solution here is to use string directly. Yeah, so if we use this, it will just, instead of passing a reference, it will copy the stack. It will just make the owner this reference to nothing instead of this. So it creates it inside, and then it passes ownership to the object or variable that's in a scope above. Okay. The rules of references, let's recap. At any given time, you can have either one mutable reference or any number of immutable references. References must always be valid. And next, let's look at different kind of references, slices. I think I'll stop here. We'll continue next time from slices. Let that sink in. Think about it a little bit. Thank you, and see you next time.